In this video, we're going to continue looking at differentiation, and we're going to follow the same theme that we've taken with all of our new things we've introduced, like limits and continuity, and we're going to look at how it applies to combinations of differentiable functions. So we'll do an algebraic differentiability theorem, which lets us add, subtract, multiply, and divide differentiable functions, and then we'll also look at composition of functions, which is the chain rule that you will have met before. So we'll begin with our algebraic differentiability theorem. This is the one that just lets us look at sums, products, scalar multiples, and quotients of differentiable functions. So the setup is very straightforward. We've got two functions defined on the same interval and assume they're both differentiable at the same point of the interval. Now the first one just says that the derivative of the sum of the two functions at C is just the sum of the derivatives. That follows directly from the algebraic limit theorem for functions. Okay, we just noting that the derivative is just a particular limit, then sums of limits add in the same way. For part two, we have the derivative of a scalar multiple of a function is just the scalar multiple of the derivative. Again, that's pretty easy to verify using the algebraic limit theorem. The remaining two, however, need a little bit more work. The first one is the product rule, which tells us how to differentiate products of two functions, and the second is the quotient rule. So we're going to prove the product rule, and we'll find that the quotient rule comes out quite easily later on, so we'll just defer the discussion of that one for the time being. Okay, so the first two are pretty straightforward exercises that you can do in your own time. The second two will focus on the product rule for now, and we'll mention the quotient rule again a bit later because it follows quite naturally from something we'll do not too far down the line. Okay, so we want to calculate the derivative of the product of two differentiable functions. So if we were to do this, we would write straight down the difference quotient that we're trying to achieve. So we're taking the limit as x tends to c of fg of x minus fg of c, all divided by x minus c. And we know that what we're trying to achieve is something involving f of x minus f of c over x minus c, and something involving g of x minus g of c over x minus c, because these are the ones that we know about, because we know these two functions are differentiable. So if we can manipulate our fraction so that we can get these terms out, then we'll be in good shape to finish it off. So the way we do this is we note that, first off, just remember that fg, that function there, is just f of x, g of x. So this expression is equal to the limit as x tends to c of f of x, g of x. Now I'm going to notice that I want to introduce terms like this. Now when we've tried to do something similar in the past, we've often found a good approach is to add something in and subtract it off again to introduce the extra pieces we want. So what I'm going to do is I'm going to pretend that f of x is going to be out the front of some expression minus g of x here, like this. So what I'll do is I will subtract a suitable term. Okay, so the f of x will come out the front and it will be nice. So it'll be g of c, so I'll get a g of x minus g of c term. Then I'll add it back on again, so that we're not changing our expression. And then I'll go minus f of c, g of c, all over x minus c. Okay, so you can see that has conveniently introduced a similar looking property over here, where we have a factor of g of c times f of x minus f of c. And likewise here, we have f of x times g of x minus g of c. So a little bit of rearranging, and we get that's equal to the limit as x tends to c of f of x times g of x minus g of c all over x minus c plus g of c times f of x minus f of c all over x minus c. Okay, and now we're in good shape because we know a differentiable function is automatically continuous, so I can just apply my algebraic limit theorems to just take the limit of these products as the product of the limits individually. So that's just going to be equal to f of c times g prime of c, because I'm just going to substitute c into x for the f one, and then plus g of c times f prime of c. And the whole thing has just come straight out for us quite naturally. Okay, so our next theorem is the chain rule, and this one has got a little bit more involved setup. Again, it's just to make sure that the two functions we're talking about are actually properly compatible. So all that stuff at the start is just talking about, we've got two functions, f maps a onto the real numbers, and g maps b onto r, where b contains the range of f. So that means if we take a number, put it into f, the output of f can then be passed into g without any issues. So that the composition g composed with f is defined. Okay, so we've set up two compatible functions so that we can use them one after the other on the same number. And then our conditions are, if f is differentiable at c, and g is differentiable at f of c, because that's what's going to be going into that, then the composition g composed with f is differentiable at c also, because c is the number that's going to go into the composition. And here is the formula for what the derivative is going to be. Okay, so we're going to need to prove this, but this is the chain rule as you have probably met it before. Now, we're not really touching the dy dx type notation in this course, so you may be more used to seeing it in terms of those, but you should be able to convince yourself that that is actually the same thing. Okay, so to get a little bit of intuition about how we're going to prove this, let's just write down what the difference quotient version, or difference quotient is going to be here. So it's going to be the limit as x tends to c of g of f of x minus g of f of c over x minus c. And you can see that we can make it into something close to the right thing by adding in an additional factor like this. So g of f of x minus g of f of c. If we make this f of x minus f of c on the bottom instead, then that looks like g prime of f of c, except there's a slight problem with this. And then we'll have that factor reintroduced on the top so that everything cancels off back to where we were before, and x minus c here. So this piece looks like g prime of f of c. This piece looks like f prime of c. But the only problem with this approach, and it is almost the right approach, and we're going to do something very similar in a second, is that this particular portion here can behave quite nastily as x goes near c. If you remember our sine of 1 over x type examples, if we have a function that has a lot of zeros in a small neighborhood of c, then that can mess this thing up. So we're going to need to create a slightly more subtle argument that's going to avoid having this f of x minus f of c on the bottom of the fraction here. So we have to just change it up slightly. But essentially this is the logic. We can write it down as these two fractions, and it's almost the right thing. The argument we're going to make is very close to this. So to actually prove it, what we're going to do is we're going to start with our g being differentiable and write down what that actually means. So g is differentiable at c, at f of c, sorry. So that means that g prime of f of c is equal to the limit. Let's make a new variable y just to distinguish it from the x that's going into f. And then as y tends to f of c, we get g of y minus g of f of c over y minus f of c. Okay, so this is what the g being differentiable at f of c means. We can write it down as a limit of a difference quotient like this one here. And we'll actually give this a name because it will be convenient to. So we'll call it d of y. So that d of y just equal g of y minus g of f of c. So it's d for difference quotient over y minus f of c. At the moment, this is not defined when y is equal to f of c, because it will put a 0 on the bottom here. But if we just make that value, if we define it to be g prime of f of c, then that makes sense, and then that will make our function continuous. So this is not defined when y equals f of c. So define d of f of c to equal g prime of f of c. That makes sense. It matches what we've written down up here, and it is going to make our function continuous because limit as y tends to f of c of d of y equals g prime of f of c, just looking at our limit statement over there. So this choice makes d continuous at f of c. Okay, so here's the trick. What we're going to now do is we're going to rearrange our expression for d of y into, so we're going to take this expression here, and we're going to bring the nasty piece in the bottom, which is where the problems were going to arise before. We're just going to bring it up into the top here. So we'll have y, so rearranging, y minus f of c, all times d of y, is equal to g of y minus g of f of c. Okay, just multiplying the bottom of the fraction up. This is true for all y in b, because we now have got rid of the bottom of the fraction issue, so that's all good. B, remember, is the set of inputs into y, and it also contains the range of f, so this includes also y equals f, and I'll make it of t, just to make it clear we're using a dummy variable. Well, no, let's just use x actually to make even more sense. Including y equals f of x. So substitute y equals f of x. And we get, I'll write it the other way around, so g, and replace this y here with f of x, g of f of x minus g of f of c equals d of f of x, that's the d factor, times f of x minus f of c. And we could also go ahead and divide this by x minus c. If we take the limit now, so now we've got a nice thing. Now take limit as x tends to c. You can see this is going to be the thing that we're actually after on the left here, the composition. And we get the composition prime, okay, it's just the difference quotient for the composition, is equal to the limit of d as we go to f of c is going to be g prime of f of c, and then we'll have f prime of c for this piece here. So this product, we can use the algebraic limit theorem to combine those two products together, and now we have the chain rule, which is great.